Okay, here's a thought experiment for you.
Oh, I like these. Go on.
Imagine you're in a pitch black room, and you see two quick flashes of light.
Okay, 2 flashes. I'm picturing it.
To your eyes, they look completely identical, just
Yeah.
flash and flash.
Right.
But one of those flashes is, let's say, totally harmless, and the other one is dangerous.
Oh, that's a bit scary. How would I ever tell them apart if they look the same?
Exactly. You would need to look at the shape of the light itself.
The shape of light.
Hello, and welcome to Simple Paper Talk. I'm Oliver.
And I am Lily. I am definitely ready to learn about this.
Today, we're going to talk about a really fascinating paper. It's a mix of physics and computer science.
Okay, that sounds like it could be difficult.
It has some big words, for sure, but we're going to break them all down. The paper is about something called pulse shape discrimination.
Pulse, shape, discrimination. Wow, that is a long phrase.
It is, isn't it?
What does that actually mean?
It's just a fancy way of saying telling two things apart by looking at the shape of their glow.
And what 2 things are we looking at today?
We're looking at things we can't even see. We're looking at invisible rays,
Invisible rays.
specifically neutrons and gamma rays.
This already sounds amazing. I'm excited to finally understand this. Let's do it.
All right, so in this paper, the scientists start with a really big problem.
Mm-hmm.
They need to find one very specific tiny particle.
And what particle is that?
It's called a neutron.
A neutron. Okay, why do they want to find neutrons? What's so important about them?
Well, neutrons are super important. They're like little detectives. They can help us find very dangerous things.
Like what kind of things?
Things like special nuclear material.
You mean like for bombs?
Exactly. So if someone were trying to, say, hide that kind of material at an airport or a border crossing, a neutron detector could find it.
Oh, I see. So this is really about security and about safety.
Yeah, it's for safety and also for some really advanced science experiments. But here's the catch. Finding a neutron is really hard.
Why? Is it because they're so small?
It is small, yeah, but that's not even the main problem. The real problem is noise.
Noise. You mean like loud sounds?
Huh, sort of. It's a good analogy. In this case, the noise isn't sound, it's other particles. Neutrons are almost always mixed in with gamma rays.
Gamma rays. What are those exactly?
A gamma ray is basically a little packet of energy. Think of it like a beam of very, very powerful, invisible light.
Mhm.
And they're everywhere.
So the gamma rays are basically hiding the neutrons.
Perfectly put.
Yeah.
It's like trying to hear one person whisper in a room where 100 other people are talking loudly.
Okay, the loud talking is the gamma rays,
Mm-hmm.
and the whisper is the neutron.
Exactly. And you need a way to completely ignore all that loud chatter and just pick out that one little whisper. You have to separate them.
Okay, so how do scientists even begin to catch these invisible things? You can't just use a net.
You can't. They use a very special tool, and it's called a scintillator.
Scintillator. That's a fun word to say.
It is.
What does it do?
A scintillator is a type of material that, well, it scintillates. It lights up. When one of these rays, a neutron or a gamma ray, hits it, it makes a flash of light.
Like a light bulb turning on?
No, much, much faster than that. Think more like a camera flash. A tiny spark that happens in a fraction of a second.
Okay, a super fast flash. So if a gamma ray hits the scintillator, it flashes.
Yes.
And if a neutron hits it, it also flashes.
Yes, that's right.
Wait, how does that help? If they both make a flash, how do you know which one was which?
And that is the million-dollar question. That's what this entire paper is about.
Okay.
To our eyes, the two flashes would look identical. Just a flash of light.
So they're both just bright light and then they're gone.
Yes. But, and this is the clever part, to a special kind of camera, to a computer, they're actually very different.
Different how?
It's all about time
Mm-hmm.
and about the shape of the flash.
The shape. You mentioned that before. Can you explain that?
Of course. Let's use an analogy. Imagine you're looking up at the night sky and you see a shooting star.
Okay, I can picture that. A bright streak of light moving really fast.
Right. And what does it look like? It has a really bright point at the front, right?
Yeah.
The head.
That's the head.
And behind it, there's a tail, a faint trail of light that slowly fades away.
Yes. The head and the tail. I see it.
Well, the flash of light inside the scintillator is just like that shooting star. It starts off super bright, and then it fades out. It has a tail.
Do both the neutron and the gamma ray make a shooting star flash?
They do.
Yeah.
But, and here's the secret, their tails are different.
How are they different?
Okay, so the gamma ray, when it hits the scintillator, it makes a flash with a very, very short tail. The light just poof.
Yeah.
It disappears almost instantly.
Okay, got it. Gamma ray equals short tail.
But the neutron,
Yeah.
the neutron is different. When it hits, it interacts with the material in a slightly different way, and it makes a flash with a long tail.
A long tail. So the light from the neutron stays around for longer.
Exactly. It lingers. It fades away much more slowly.
I see. So neutron equals long tail.
You've got it. So if we can find a way to measure the length of that tail, we can tell them apart every single time.
That sounds almost simple when you put it like that.
The idea is simple, yes, but in reality, it's all happening incredibly fast. I mean, unbelievably fast.
How fast are we talking about?
We're talking about nanoseconds.
A nanosecond. What is that?
A nanosecond is 1/1000th of a second.
1/1000th. Wow, that's way too fast for a person to see.
Oh, absolutely.
Yeah.
You can't use a stopwatch for this. You need a very, very fast machine, a computer.
Okay, before we get to the machine, tell me more about the scintillator material. What's it made of?
That's a great question. And it's a huge part of the paper because they actually compare two different types of scintillator
Why two?
because they want to find out which one is better. It's like they have an old champion, the one everyone has used for years, and a new challenger.
A competition. Okay, so who's the old champion?
The old champion is a liquid. It's a chemical called EJ301.
A liquid that glows like water.
It's a special chemical liquid.
Yeah.
And for a long time, it's been the best. It's really, really good at this job of separating neutrons and gamma rays. Scientists love it for that.
So if it's so good, why are they even looking for a challenger? Why change it?
Because liquids can be a real pain. They're messy.
Messy how?
For one, this liquid, EJ301, is toxic. That means it's poisonous if you touch it or breathe it in. And it's also flammable, so it can catch fire.
Oh, that sounds pretty dangerous to work with.
It can be. You have to be very careful. And that's not all. Liquids can leak. Imagine you build this expensive detector, and it cracks and spills poisonous liquid everywhere.
That would be a disaster.
Right. And there's another weird problem. Liquids expand and contract when the temperature changes.
Like water boiling in a pot.
Exactly. So if it gets hot, the liquid expands. To stop the container from bursting, they have to leave a little air bubble inside.
A bubble.
Yes, an expansion bubble. But what happens if you turn the detector on its side or upside down?
The bubble moves.
The bubble moves. And if it moves into the path of the light, it can completely ruin your measurement.
So the liquid is great at the science part, but it's just not very practical or convenient.
You've nailed it. Okay, so now let's talk about the challenger. The new material.
I'm ready. What is it?
It's a solid crystal. Its name is stillbean.
A still bean. Is it like a rock?
Uh.
Or a diamond?
It's what's called an organic crystal. It basically looks like a very clear piece of plastic or glass.
And it's solid, right?
Completely solid. It's hard. It can't leak. It doesn't need bubbles.
That already sounds so much better.
It's definitely safer and easier to handle. But, there was a big problem with stillbean in the past.
Oh. What was the problem?
It was incredibly difficult and expensive to make big, high-quality crystals.
Why was that?
Well, the traditional way to make a crystal is called melt-grown. You melt the raw material down and then let it cool very, very slowly.
Like making ice cubes from water.
Exactly like that. But
That's
stillbean is fragile. It doesn't like being melted. It tends to crack and break apart.
So they could only make really small, expensive crystals.
Correct. They were too small and too expensive for most applications. People knew it was a good material, but they just couldn't make it properly.
So what changed? Why are they testing it now?
Because the paper talks about a brand new way to make them. It's called the solution-grown method.
Solution grown? What does that mean?
It means instead of melting it, they dissolve the stillbean powder in a liquid, kind of like dissolving sugar in water. And then over a long time, they let the crystal grow slowly out of that liquid.
Oh, like making rock candy. Growing sugar crystals on a string in a jar.
That is the perfect analogy. It's exactly like that. And this new method lets them grow huge, perfectly clear crystals. And it's much cheaper.
So now we have this amazing solid crystal, and it's actually easy to get.
We do. So the big question for the scientists is this new solid stillbean crystal just as good as the old champion, the liquid?
It's the competition, crystal versus liquid.
Exactly. Can the stillbean separate those long tails from the short tails just as clearly as the EJ301 liquid can?
So how did they test it? What was the experiment?
They took one of each scintillator to a laboratory and set up a very careful experiment.
What did the setup look like?
They put the scintillator on a table connected to all the electronics, and then they put a small, safe source of radiation near it.
How near?
The paper says 25 centimeters away.
Okay, so about the length of a school ruler.
That's right. And they used two different radiation sources. First, they used something called cesium-137.
Cesium-137, what does that one do?
It's a special source because it only shoots out gamma rays, no neutrons at all.
Why would they want only gamma rays? I thought the point was to separate them.
It was a practice run. They needed to calibrate the machine.
Calibrate, what's that?
It's like setting the rules for the game. They needed to measure lots of gamma rays first to teach the computer, hey, this is exactly what a short-tail flash looks like.
Ah, okay, like showing the computer a reference picture. This is a gamma ray.
Precisely. They look for a specific feature on the graph called the Compton edge.
Compton edge. Sounds cool.
It's just a reference point. It helps them make sure they're measuring the energy of the flashes correctly.
Okay, so they practiced with the gamma rays. What came next, the real test?
The real test. They brought out a different source. This one is called Californium-252.
Californium, like the state in the U.S.
Exactly. It was first discovered at a university there.
Yeah.
And Californium-252 is very special for this kind of work
Why is that?
because it shoots out both neutrons and gamma rays at the very same time.
So it creates that perfect noisy room you were talking about.
It's the perfect test case. Now, the detector has to deal with the whisper and the loud chatter all mixed together. Can it tell them apart?
And what did they use to actually read the flashes? You said it was a fast machine.
They used a tool called a digitizer.
A digitizer. Sounds digital.
It is. See, in the old days, scientists used what are called analog electronics.
Like an old radio with a dial.
Kind of like that, yeah. Analog systems were clever, but they were slow. And if too many flashes happened at once, the machine would get confused.
It would get overwhelmed.
It would.
Yeah.
But a digitizer is basically a tiny, super fast computer. It doesn't just see a flash, it takes a digital picture of the entire light wave.
It takes a photo of the flash.
A very detailed one. It turns the light, the shape of the wave, into a long list of numbers.
And computers love numbers.
They do.
Yeah.
And this digitizer is ridiculously fast. It takes 500 million samples. Like 500 million tiny pictures every single second.
500 million? That's just, I can't even imagine that.
It's so fast that it allows them to see the shape of that nanosecond-long tail in perfect detail.
Okay, so they have the scintillator, they have the radiation source, and they have the super fast digitizer. What did they do next?
They let it run. They collected thousands and thousands of these flashes. Then they took all that data, all those numbers, and used math to analyze it.
Is the math really complicated?
The math itself is. But the idea behind it is very clever and easy to understand. They actually used two different methods.
Okay, what was the first method?
The first one is called charge comparison.
Charge comparison, what is it comparing?
It's comparing the amount of light in different parts of the flash. Remember our shooting star analogy?
I do. The bright head and the long fading tail.
Okay, so for each flash, the computer first measures the total amount of light in the whole thing, the head and the tail together.
The whole star, got it.
Then it does a second measurement. It only measures the light in the tail part.
Just the end bit.
Just the end bit, after the bright peak has passed. Then it does a simple division. It divides the amount of tail light by the amount of total light.
So it makes a fraction, or a ratio.
Exactly. Now think about it. If that fraction is a big number, what does that mean?
A big number means there must be a lot of light in the tail compared to the total.
And a lot of light in the tail means?
A long tail, which is a neutron.
You've got it.
And if the fraction is a small number,
then there's not much light in the tail. It's a short tail. And that means it was a gamma ray.
that is really smart. It's just a simple comparison of sizes.
It is. The paper mentions they had to be very careful about one thing, though. They had to choose exactly when to start measuring the tail.
The start time for the tail measurement?
Yes. If you start measuring too early, you'll accidentally include some of the bright head, and then all the flashes look the same.
And if you start too late,
The light might be all gone, and you just measure nothing.
so they had to find that Goldilocks spot, the perfect time.
They did. And they found, for the still beam crystal, the perfect time to start was 36 nanoseconds after the flash began.
That is incredibly precise.
For the liquid, the EJ301, the best time, was slightly different. It was 32 nanoseconds.
Interesting. So the liquid's flash is a little bit faster overall.
It seems so, yes. A tiny bit.
Okay, what about the second math method?
The second one is called constant time discrimination.
That's an even bigger name.
Let's just call it CTD. This method is a bit different. It's more about the shape itself, not the total amount of light.
How does that one work?
Okay, imagine you have all of your shooting star flashes. Some are from very strong rays, so they're big and bright. Some are from weak rays, so they're small and dim.
Okay, a mix of big and small flashes.
Right. For this method, the computer digitally stretches or squishes all of them so their peaks are all the same height.
It normalizes them, makes them
Yep.
all equal at their brightest point.
Exactly. Now that they're all the same height, you just look at one specific point in time on the clock.
Okay.
And at that specific time, you just measure the height of the line. Is it still high or has it dropped down low?
I think I get it. If it was a neutron with a long, slow tail, the line should still be pretty high up at that time.
Bingo. And if it's a gamma ray with a short, fast tail, the light has already faded, so the line will be very low, close to zero.
So they're just checking the height at one specific moment in time.
That's all it is. And both methods worked really well.
Was one method better than the other?
They gave very similar results in the end. The paper suggests the charge comparison method is a bit simpler and maybe faster for a computer to do in real time.
Okay, so now for the big results. The moment of truth. Who won the competition? The crystal or the liquid?
To declare a winner, they use a special score. It's called the figure of merit.
The figure of merit. Is a bigger score better?
Yes, a bigger score is much better.
Yeah.
Imagine you plot all your results on a graph. All the gamma rays make one little hill or pile,
Okay.
and all the neutrons make another little hill.
Right.
What you want is for those two hills to be as far apart as possible. You want a big, clear gap between them so there's no confusion.
The gap shows how well you can separate them.
Yes. The figure of merit is just a number that measures how wide and clear that gap is.
What's considered a good score?
A score above 1.5 is usually considered excellent separation. It means the two hills are completely separated with a clean valley in between.
So did the solid still being crystal get a 1.5?
The stubborn crystal got a score of 1.70.
Wow, 1.70, that's really high. It easily passed the test.
It's an excellent score. Absolutely fantastic performance. Now, what about the old champion, the liquid?
What score did the liquid get?
The liquid scintillator, EJ301, got a score of 1.79.
Oh. So 1.79 is higher than 1.70.
It is just a little bit higher.
So the liquid is still the technical winner.
On paper, yes, by a very small margin. The paper explains that the liquid produces a little bit more light overall for each flash, which just makes the picture a tiny bit clearer for the computer.
But hang on, you said the liquid is toxic and flammable and it leaks and it has bubbles?
And that is the most important point of the whole paper. The liquid is a tiny, tiny bit better on the scorecard. But the solid crystal is so much better in every other way.
It's safer, it's more stable.
Exactly. The scientists say that a score of 1.70 is already so good, it's more than good enough for almost any application you can think of.
So the conclusion is that we can switch to the safer solid crystal and not really lose any performance.
Absolutely. The scientists say that this new solution, grown still bean, is a fantastic and viable replacement for the old liquid scintillators.
That's really good news. We can have the safety without using poisonous materials.
It really is. And there was one more thing they tested, which was very important. They tested different energy levels.
Energy levels, what do you mean by that?
Well, sometimes the incoming rays are very strong, very high energy, and sometimes they're weak or low energy.
So it's like the difference between a loud shout and a very quiet whisper.
That's a great way to put it. It's always easier to tell things apart when the signal is big and loud. The real challenge is, what happens when the signals are quiet?
Is it harder to see the shape then?
Much harder. If the flash of light is very dim to begin with, seeing the difference in the tail shape is tough.
So did the crystal still work for those weak, low-energy signals?
It did. They tested it with very low energy rays, and the figure of merit score stayed high. It was still excellent.
That's really impressive.
And this is critical for the next step, for what they want to build with these things.
Which is what?
They want to build cameras.
Camera, you mean we could take a picture of neutrons?
That is the ultimate goal. They want to build something called a dual particle imager.
Dual means two.
Yes, a single camera that can take a picture of where the gamma rays are coming from, and at the same time, a picture of where the neutrons are coming from.
That would be like having superpower vision.
It really would. You could point this camera at a big shipping container, and you might see the whole thing glowing with gamma rays, but then see one specific spot glowing with neutrons.
And knowing the difference is everything.
Everything. Because if you just see gamma rays, it could be harmless. It could be a shipment of bananas or even kitty litter.
Wait, bananas are radioactive?
A tiny, tiny bit.
Mhm.
It's natural. But if you see a strong source of neutrons, that's a huge red flag. That could be a weapon.
So the camera has to be able to tell the difference instantly and reliably.
Instantly. And because these new crystals are solid and safe, they can build these cameras to be portable.
Right, you can carry them around without worrying about spills.
You can put them on trucks, on robots, you can carry them in a backpack. This paper is so important because it proves that we have the right materials and the right math to build these amazing new tools.
It's just incredible how much science goes into seeing one tiny flash of light.
It is, isn't it? It's
Yeah.
a combination of chemistry to grow the crystal, physics to understand the flashes, and computer science to analyze them in real time.
And it all comes together to turn invisible danger into clear, visible numbers on a screen.
That is a perfect way to summarize it. That was a deep story. Let's quickly review some of the key words to make sure they stick.
Good idea.
Okay, the first word is neutron.
A neutron is a tiny particle. It doesn't have an electric charge, and it makes a long flash of light in the scintillator.
Perfect. The second word is gamma ray.
A gamma ray is a little packet of pure energy, like a very strong, invisible light beam, and it makes a short flash.
Excellent. The third word, the fun one, scintillator.
A scintillator is that special material that glows or flashes when radiation hits it. It can be a liquid, or in this case, a solid crystal.
Number 4 is pulse.
A pulse is just that single, quick flash of light that the scintillator makes, and we look at its shape.
Great. Number 5 is discriminant.
To discriminate just means to tell the difference between two or more things. In this paper, we discriminate between neutrons and gamma rays.
And the last one, number 6, is tail.
The tail is the final part of the light flash. It's the part that slowly fades away, and the neutron has a long tail.
Fantastic. Okay, are you ready for a very quick mini quiz to see what you remember?
I think so. Let's do it.
Question 1. What are the two invisible things that the scientists are trying to separate?
Oh, that's easy. They're separating neutrons and gamma rays.
Correct. Okay, question 2. Which of the two materials they tested is safer to use, the liquid or the solid crystal?
The solid crystal, the still beam, is much safer. It's because it can't leak and it doesn't have those tricky bubbles.
That's exactly right. And the final question, number 3. Which particle creates the flash of light with the long tail?
The neutron has the long tail. That's the secret to finding it.
Perfect. You got all 3 right. Excellent work. So today we really explored the shape of invisible light. We learned that even though they look the same to us, neutrons and gamma rays make very different shaped flashes in a special crystal.
And we learned that these new solid crystals, grown from a solution, are almost as good as the old messy liquids, but they're so much safer and more practical to use.
And by using super fast computers to measure the tail of that light, scientists can tell them apart. And that helps keep us all safe and helps us do amazing science.
Thank you so much for explaining all that. I really feel like I get it now.
You are very welcome. It was my pleasure. And then thank you all for listening to Simple Paper Talk.
We'll see you next time. 5 keywords, 6 items. 1 neutron. 2 gamma ray. 3 scintillator. 4 pulse. 5 discriminate. 6 tail. 6 mini quiz. 3 Q&As.
What are the two invisible things we are separating?
Neutrons and gamma rays.
Which material is safer to use, the liquid or the solid crystal?
The solid crystal, still beam.
Which one has a long tail of light?
The neutron.